I was posting this question on Facebook, so I thought I'd give it a quick spin. Rather than get my full setup and go out in my classroom, I just thought I'd record something here on my desk. So I thought I'd give it a go because it's an interesting question. It's got some challenges to it. This is all I was given. I wasn't given a domain, so this could be a general solution question, but I'm gonna just treat it. I'm just gonna give it a domain like say 0 to 360, because that's a pretty sort of standard domain to assume. If this is a general solution question, then for the person who submitted it, maybe you can let me know and I'm happy to adjust it, though most of the steps will be basically the same, and it's really the way that you articulate the answer that is a bit different. But anyway, let's move on with it. Now, what makes this challenging is that you've got this this angle up here, x on 2, and this x, and they don't sort of play very nicely together with each other. It's hard to make these two trig functions interact with each other, so you can simplify it. So therefore, I'm going to use my double angle results to rephrase this question in a way that gets everything in terms of one trig function rather than sines and cosines. I'm going to convert it all into sines, as you'll see in a second. So the first thing I'm going to do is say, introduce a new angle. Let's call it theta. So let's let theta equal x on 2. Okay, so that implies obviously that this x up here, that will be 2 theta. Okay, so I'll use that in a second. Before I actually make the substitution, I should note that if I'm solving for theta, which is x on 2, I'm going to solve angles for theta, and that's going to give me, angles in degrees that are actually in a different domain. Because x on 2, if I divide this entire domain by 2, you go from 0 to 180, not 0 to 360. So I'll just note that down. It's always good to note down restrictions earlier rather than later, so you don't forget it for later on. Alright, now, with this substitution, how does that change my original equation? Well, it's going to make it look like this. I'll have 6 sine theta minus cos 2 theta, and that's equal to 0. So what can I do with that? Well, this cos 2 theta part, it's easy to get that in terms of sines using your double angle formula. So that's going to actually look like, I'll do it long form just in case you're not so familiar with this identity. That's going to be cos squared theta minus sine squared theta. That's the standard way to expand it. But you may also remember that sine squared theta is, I actually want to get rid of the cos. Cos squared theta is 1 minus sine squared theta on its own using the Pythagorean identity. So if I change that into 1 minus sine squared, and I've got a minus sine squared here on the end as well, that's going to become 6 sine theta minus 1 minus 2 sine squared theta. Okay, so that's nice. Now that I've got everything in terms of sines, I can start to actually solve this. You can see it's a quadratic equation in sine. So if I move up a little bit, let's keep going. If I turn this around a little bit, you can see, just to make it more obvious, what my coefficients are. That negative will cancel out, so it'll be 2 sine squared theta plus 6 sine theta minus 1. Now when you look at that, you look at these coefficients, they're not going to factorize neatly, so you might as well save yourself the effort and just go straight into the quadratic formula. So we're used to things being, 2x squared plus 6x minus 1. Well, in this case, you've just got sines instead of x's, so you can use the quadratic formula just the same way that you would normally do it. Instead of x equals the quadratic formula, you're going to have sine theta equals the quadratic formula. So that's going to be minus b, which is 6 in this case, plus or minus the square root of b squared, that's 36, minus 4ac. Minus 4 times minus 1 times 2, that's going to give me 8, all over 2a, which is 4. Okay, so simplifying that out a little bit, you're going to get minus 6 plus or minus, that looks like 44 to me, all over 4. Because there's a 4 out of there, I can simplify that third. Take a factor of root 4 out, which is actually 2. So that gives me that. So this, I can simplify a little bit. I'll just move this up here. You can still just see that, I think. So what's that going to become? Well, I'll just take out the factor of 2. So minus 3 plus or minus root 11 on 2. Okay, now, you look at that, and that doesn't seem too bad, but there's some problems with it, which are not that obvious when you're looking at it in third form. So let me evaluate it. Let me get some. This is our solutions for sine theta. Let me evaluate it, and you'll see there's an issue. If you get your calculator out, and you take the approximation of these two answers, one of them is obviously the negative solution, and the other one is the positive solution. Okay, so your calculator will tell you that this first one is about minus 3.16, and the second one's about 0.16. Okay, and you can see your problem. Sine theta, right? What does it look like? Well, just as a graph, it looks like this. Okay, and it goes on forever. And this range here of sine is from -1 to 1, right? Sine can never go outside that unless you change the coefficient out the front to make its amplitude greater. So sine theta is always between -1 and 1. Therefore, this minus 3.16 is never a valid solution. There's no value of theta that you could put into this equation to satisfy it, right? So since this restriction exists, therefore, sine theta is only equal to 0.16. That's the only valid solution, okay? So when you take that and pop it into your calculator to get sine inverse, you're going to get this. You're going to get two solutions, 9 degrees and 7 minutes. I'm approximating again, so I should put that in. Or 170 degrees and 53 minutes. Okay, so you're looking at that, and those both fit within the domain restrictions we've already noticed, so that's great. The last thing to realize is that we weren't solving for theta in the first place. Our original equation, it was all in terms of x, right? Like this. So since I introduced theta to solve my equation, I should get rid of theta so that I can actually produce the final equation in terms of x. So if I come back over here, the original thing I said was that theta is x on 2, right? So now, to actually get x, I just have to multiply my answers by 2. So I guess that would give me, sorry, I actually should have worked this out earlier. Well, this one's obvious. That one's not so hard. Sorry, that's 18 degrees and 14 minutes, I think. And this second one will become, let's just punch in the numbers. Got to be careful with these minutes over here. 341 degrees, 46 minutes. And that's my solution between 0 and 360.